Hello, in this chapter what we're going to be discussing aqueous solutions. And eventually what we're going to be getting to is concentrations. At what concentration do certain salts dissolve into an aqueous solution, which would be water. Once again, this is going to be a rather calculation heavy chapter and just a lot of calculations. So I'm going to work through some of these calculations, not right now, but we will get through some of these calculations in a few moments. I'll be more towards the end of this little talk. So once again, if you happen to have any questions, let me know. All right, so for the first question here asked is, write a balanced equation for the dissociation of each of the following strong electrolytes in water. Now, a strong electrolyte is going to be a salt that is going to dissolve into water. And what you have here is you have lithium bromide, you have sodium nitrate, you have copper 2 chloride. The reason it's called copper 2 chloride is because the copper has a +2 charge. If you look on the periodic table as to where copper occurs on the periodic table, it's in that transition metal area. And so we really don't know the charge because of where it's located on the periodic table. And so what you have to do is you have to look at the anion. And so you recognize that the anion is a chloride. Chloride is a halogen, so it's going to have a charge of -1. Right? You happen to have 2 of those, so that means that the whole chloride portion of the molecule is a -2 because each chloride is a -1. And so in order to make this neutral, if this whole side is going to be -2, then this has to be +2, and thus it's called copper 2 chloride, and the 2 represents the charge on the copper. And this is potassium carbonate. So these are all going to be ionic because you have a metal and a nonmetal. All right? So when you have a metal and a nonmetal bonded together, that's going to be an ionic substance. All right? And such that the metals, so that's going to be the ones written here on the left-hand side, those are going to be the metals. All right? They're going to give up the electron to the nonmetal. All right? To the nonmetal. All right, so what we're going to do is we want to write a balanced equation for the dissociation of each of the following strong electrolytes in solution. Strong means that they completely break apart. All right, and so lithium bromide is going to break apart into water, so this would be a solid, and it's going to break up into lithium +1 because of where it's located on the periodic table, and that's going to be aqueous, meaning it's soluble in water, and then the bromide as such. All right. Sodium nitrate, all right, this is the nitrate polyatomic. That stays together. It does not break apart. And so this is going to break apart, it's going to dissolve into sodium cation, and that's going to be aqueous. Plus, now if you didn't know the charge of the nitrate, but all of this here is going to be the anion. If sodium is +1, then the nitrate has to be -1. So that's going to be nitrate, NO3 minus aqueous as such. Now I got done explaining the copper a little bit. This is going to be the copper 2 chloride. This is going to break up or dissolve or dissociate into copper 2 plus aqueous plus, now this becomes 2 chlorides, and they're going to be aqueous. All right. Typically, you don't write the 2 down here. You write up here meaning that there's 2 individual ions of the chloride. Here, you have the potassium. And if you notice where potassium is located on the periodic table, it's going to be in the very first column. You have 2 of them. Because it's in the first column, it's going to have a +1 charge. And this will be aqueous plus. Now, if this is all going to be +2, then the chloride portion, the carbonate portion of this has to be -2. And so this is a polyatomic once again, so that becomes CO3, 2 minus, and that's going to be aqueous as well. I think the harder things about this are 2 things. You've got the copper, which is a transition metal. That's going to be a +2. You have to know that by looking at the anion. And then these polyatomics are a little bit more difficult. All right? Now for this next problem, what we're going to be working with is we're going to indicate the number of equivalences in each of the following. All right? So for the first one, if we happen to have 1 mole of magnesium each mole of magnesium, because it's a +2 ion, is going to contribute 2 equivalences of charge. So this is going to be equal to 2 equivalences. For part B, we have hydroxides. Now each mole of the hydroxide is going to contribute 1 equivalence. All right. So for each mole of the hydroxide, 1 equivalence of charge is going to be represented. It doesn't matter whether it's plus or minus, but if we happen to have 2 moles of hydroxides, then this is going to be equal to 2 equivalents. All right. Here we have 4 moles of the chloride. Each mole of chloride is going to contribute 1 equivalence of charge. If we happen to have 4 moles of chloride, and I guess another way we could write this is we could say that 1 mole, oops, we don't want to do that. For every 1 mole of chloride, there's 1 equivalence of charge. All right. Now, if we happen to have 4 moles, all right, then the moles cancel and we're left with 4 equivalences. All right. Down here for the iron, each mole of iron is going to contribute 3 equivalences of charge. All right. So we have 3 equivalents of charge for every 1 mole of iron. And where I'm getting the 3 from is from the charge right there. All right. We have 2 moles of iron, so the moles cancel, and we get 6 equivalences of charge if we happen to have 2 moles of iron 3 ions. All right, so now for the next problem, what we're going to do is we're going to a solution to replace potassium ions contains 40 milliequivalents per liter each of potassium as well as chloride. How many moles of each of the potassium and the chloride are in 1.5 liters of solution? Right? They're going to be 1.5 liters of solution. All right. So let's first write down the information that's given to us. So we happen to have 40 milliequivalents per liter of the potassium. All right. And likewise, we'll get to the chloride in a little bit. But what we want to be able to calculate is the number of moles of potassium in this. Now remember, milli means 1,000th of an equivalence. All right. And so if we first calculate that, we're going to say 1 equivalent is equal to 1,000 milliequivalents. All right. So the milliequivalents cancels. We're now in the units of equivalence. Okay. And we know that for every 1 equivalent, we have 1 mole of potassium. Now there's a table in your book that will give you the number of equivalences per mole of ions. All right. Now the equivalents will cancel, and so now we're in moles of potassium. However, we still have this liter. What are we going to do with the liter? Well, to get rid of the liter, we're going to simply multiply by the volume that was given in the problem. The problem asked for 1.5 liters of solution. So liters cancel. And so now in order to calculate this, you take 40 times 1.5 divided by 1,000. And the units that we have are going to be moles of potassium. And if we do this arithmetic, we get 0.06 moles of potassium. All right. Now the second part of the problem that states that we have 40 milliequivalents of chloride per liter. All right. And we're going to go through and do the exact same calculation we did before. We're going to convert the milliequivalences to equivalents. All right. Then we're going to multiply, convert the equivalent into moles of chloride. And so there's 1 equivalent is equivalent to 1 mole of chloride. Or you can say 1 mole of chloride is equal to 1 equivalent. So our equivalents cancels, our milli-equivalents cancels, however we still have this liter. So if we multiply it by the volume that's given in the problem, 1.5 liters, our liters cancel, and now we will take 40 multiplied by 1.5 divided by 1,000, and we're going to get the exact same number we got over here. All right. Next problem what we're going to be looking at is we're going to be looking at concentrations, okay? And more specifically, we're going to be looking at volume per volume and mass per mass. So this question states, what is the difference between a 10% volume by volume methanol solution as opposed to a 10% mass by mass methanol solution? All right? So let's just look at the first part. We'll look at the 10% or the 10% volume by volume methanol. So if we start with 10%, we're going to do volume by volume of a methanol solution. So what this says, for instance, is that another way of stating this is that if it's 10%, all right, we could say that there's going to be 10 milliliters of methanol in 100 milliliters of solution, right? That would be a 10% volume by volume methanol solution. As opposed to if we have a 10% mass by mass of methanol. And what that means is that we're going to have 10 grams of methanol in 100 grams of solution. So that would be the difference. And so what this really boils down to is it boils down to the density of both the methanol as well as the water. But these are different calculations, different amounts, because you have a volume by volume as opposed to a mass by mass. In this next question, what we're going to be tackling is we're still going to be working with concentrations. Okay. So next one, this question asks, calculate the mass percent. So that's going to be mass per mass, right? So the mass of the solute or the mass of the solution of the solute in each of the following. So in the first one, we happen to have 75 grams of sodium hydroxide in 325 grams of solution. So that solution is going to contain the sodium hydroxide as well as the water. All right. And so to calculate the mass percent of the sodium hydroxide in this solution, we're going to take 75 grams of the sodium hydroxide, divide that by 325 grams of solution, and then we'll multiply it by 100 to convert that into a percent. And if we do that arithmetic, we get 23%. All right. For the next problem, we happen to have, oops, excuse me, I gotta look at my notes real quick. We are going to have, so for B, we have 2 grams of KOH in 20 grams of water. Now, once again, we're going to take the mass of the solute, so it'd be KOH, and we're going to divide it by the mass of the solution. Well, the mass of the solution is going to be the 20 grams of water as well as the 2 grams of potassium hydroxide. So the mass of the solution is going to be the 20 plus the 2. And so that gives us 22 grams of solution. Now in the previous problem up here, this gave us the mass of the solution. Okay? Here, it didn't give us the mass of the solution. It gave us the mass of the solute and the mass of, the mass of the solvent and the mass of the solute. And so the mass of the solution is going to be the mass of the solvent plus the mass of the solute. If we multiply that by 100, this is going to give us 9.1%. All right. Let me do a little bit of erasing before we continue on. But it's important to know whether the problem is giving you just the solute and solvent, or if it's giving you the mass of both the solute and the solvent. So for instance, the first problem, we had the mass of the solution. In the second problem, we had it separated, we had the mass of the solute as well as the mass of the solvent. So the mass of the solution, the two of them combined, is going to be equal to the mass of the solute and the mass of the solvent. It's going to give you the mass of the entire solution. So it's important to know those numbers and to read the problem very carefully. I tend to get in a hurry and miss some things. All right. So part C, all right, so part C, we have, this is going to be 48.5 grams of sodium carbonate in 250 grams of solution. All right, so once again, we want to find the mass percent of that. So we're going to take the mass of the solute, so that's 48.5 grams of sodium carbonate, divided by the mass of the solution. Now the solution, once again, is going to contain water and the sodium carbonate. And so that would be 250 grams of the sodium carbonate multiplied by 100. And what we get for that is we get 19.4%. All right, because it's the mass by mass. So I should probably put over here mass per mass to make it more complete. And so what this is saying is it's saying that 19.4% of this solution is going to be sodium carbonate. All right, in this next question, what we're going to be dealing with is we're going to be dealing with mass per volume solution. Once again, we're going to continue to working on problems of concentration. So in this first question, what we have is we have 2.5 grams of lithium chloride and 30 milliliters of solution. And this question asks us to calculate the mass volume percent for the solution, for the solute in each of the following. So we need to find the percent mass by volume. All right. So what we're going to do is we're going to take our mass of the solute, the lithium chloride is going to be our solute, and we're going to divide that by the volume of our solution. So this is going to be 2.5 grams of the lithium chloride in the 30 milliliters of solution. And if we multiply this obviously by 100, that's going to give us a percent. And so that percent is going to be 6.25%. All right. Now the next problem for this is we happen to have 7.5 grams of casein, and that's going to be in 120 milliliters of milk. So we're going to divide our mass of solute divided by the volume of the solution. So this is 7.5 grams divided by 120 milliliters, and we're going to multiply that by 100. And if we do the arithmetic there, we end up getting, once again, 6.25%. Now this just happens to be a coincidence. Not all these are equal to 6.25%, but this just happens to be a unique situation or a coincidence. All right. We're going to continue doing problems that have to deal with concentrations or of solutions. Right. In this case, what we have is we have an 11. What we're wanting to do here is we're wanting to generate a 11% sulfuric acid solution from a 10 milliliters of sulfuric or 20% sulfuric acid solution. So obviously, in order to make an 11% from a 20%, we're going to have to do a dilution. All right, and the equation for the dilution is C1V1 is equal to C2V2. And what C1 is that's going to be the concentration of the stock. Now this is the stock. This is what it's coming from. So C1 is going to refer to the greatest concentration, which is what this is. C2V2 is going to deal with this portion, and that is the dilution. All right? So we want to know, we want to determine the final volume. How much of this, of an 11% solution, are we going to make if we start with a 10 milliliters of a 20% sulfuric acid solution? So C1V1 is the stock. So C1 is going to be the 20%. All right. V1 is going to be the volume. So that's going to be 10 milliliters. C2 is going to be the dilution. And so that's going to be the 11%. And V2 is ultimately what we're looking for. So V2 is going to be what we want to solve for. So in order to solve this equation, we're going to have to divide everything by 11%. And so what we end up getting here is we end up getting 20% times 10 milliliters divided by our 11% is equal to V2. And what happens with the units now is that the percents cancel and we're left in units of milliliters. And so when we go through and do this arithmetic, what we end up getting is we get V2 is equal to 200 milliliters. All right? And so that's all that these questions are pertaining to, all right? They're simply going to be dilutions, all right? And we're going to use the exact same equation that we just got done doing. C1V1 is equal to C2V2. Now the concentration as well as the volumes can be of any unit you want. They do not have to be percentages. They do not have to be in the metric system. This will work very well with molarity. It works very well with any kind of percent. It works just as well with any of the volumes. You do not necessarily have to use the liters. You could use milliliters as we did in this equation. You could use gallons, you could use quarts, you could use cups, you could use teaspoons, tablespoons, whatever type of measurement you want to use, or any type of volume you could possibly use. You could use cubic inches, cubic feet, you could use cubic meters, cubic yards, cubic centimeters. You kind of get the hint, right? Any type of volume you want to use will work for this, all right? So what's the next one say? The next one says that we are going to make, so this is B is going to be 0.1 molar, all right, of an HCl solution. And it's going to be from, what are we going to make this from? We're going to make this from 25 milliliters of a 6 molar HCl solution. So once again, we're going to use the exact same equation used before. We're going to use C1V1 is equal to C2V2. All right. Once again, the C1s and V1 are going to deal with the stock. So the concentration of this is going to be 6 molar. The volume is 25 milliliters. And C2 is going to be our dilution. And the concentration is going to be 0.1 molar. And V2. Once again, we're going to divide by 0.1 on both sides, such that we find out that V2 is going to be equal to, or I'll just write it out for you, it's going to be 6 molar times 25 milliliters divided by, now, our 0.1 molar. Our molarity cancels. We're left in units of milliliters. And this volume is going to be equal to 1,500 milliliters. All right. So if we take 25 milliliters of a 6 molar HCl solution and we dilute it to 0.1 molar, we're going to generate 1,500 milliliters of solution. All right, D. Okay, and we're going to have 11% mass by volume of calcium chloride, and this is going to comes from 18 milliliters of a 40% mass by volume solution. Sorry, I ran out of room there. We're going to use yet once again our favorite equation, the dilution equation. C1V1 is equal to C2V2. And we're just going to fill this stuff in. C1 is going to be 40%. Our volume of that is going to be 18 milliliters, is equal to now the concentration of the dilution times V2. Once again, we'll divide by our 11%, and V2 is going to be equal to, and you can see what's going to happen to that cancels. That'll cancel that side. And what you can see here now is that the percent cancels, and once again, we're going to be left in milliliters. And so we do this calculation, what we end up getting is we get 72 milliliters. So if we start out with 18 milliliters of a 40% mass by volume solution of calcium chloride, and we're going to dilute that to 11%, we're going to end up with 72 milliliters of the 11% mass by volume of calcium chloride. Now, what we've done in this problem is we worked with mass by volume, we've worked with molarity, and the equation doesn't change. We use the exact same equation over and over. So as I stated, the concentration doesn't matter. All right, what concentration you use? You can use mass by mass, you can use mass by volume, you can do volume by volume, you can do molarity. You can use any unit of volume that you want. It doesn't matter. It'll work itself out in the end. If you happen to have any questions on these on aqueous solutions or on these concentration calculations, please let me know.